Okay, hello everyone. Welcome to this video. In this video, we're going to talk about a little things of control theory. So we begin. A departure point, a departure point of control theory is the differential equation, is the differential equation y prime equal f of y and u, and y of 0 equal x, an element of R m. Perfect. With the right, with the right hand side, depending on a parameter, u from a set u uppercase subset of Rm. This set u uppercase, this set u is called the set of parameters. The set of parameters. Okay, the differential equation depending on a parameter have been objects of the theory of differential equation for a long time. In particular, the question of continuous dependence of the solution has been asked and answered under appropriate conditions. Problems studied in mathematical control are of different nature. A basic role in the formulation is the concept of control. But where is a control? Okay, a control basically is a function. We have a control basically is a function, but we can call a control in two ways. We can call it open loop and closed loop. Okay. Why are they different? Okay, what is an open loop? An open loop is a function defined from 0 to infinity in this interval to the set of parameters such that y prime of t equal f y of t, u of t, t greater or equal than 0, and y of 0 equal x has a well-defined solution. Okay, well, in this case, we have an open loop. It's a function that satisfies such that this system has a well-defined solution. We have to consider something, that this x, that is the initial condition, we are going to call it an state. That in this case is an initial state. Controls called open loop are also called strategies or inputs. Well, and we have that for open loop. So what are the closed loops? The closed loops can be identified with a mapping key from Rn to the set of parameters U, such that this system y prime of t equal f y of t key y of t, where t is greater or equal than 0 and y of 0 is equal to x, has a well-defined solution. Okay, this function key, okay, let me move there. Okay, this function key is called a feedback. It's called feedback. It's called feedback. Okay, the controls that are classified as closed loops are also called outputs. Okay, we can make a visual representation about this. We can imagine an open loop or something like this. We have an input. Okay, then we have our control function. Then we have a process. Where in this case, this process is the differential equation y prime equal f yu. Okay, and then we have a result that in this case is the result of the differential equation. But in the basic sense, what is an open loop? An open loop carry a state A from a state a state A, carry a state A to another state, state B. Okay, and well, the closed loop are something like this. We have an input, then we have a control. Again, we have a process. Okay, we have a process, and we have an output. Why? But in this representation, we also have a feedback. That is something like this. U equal key of y. Okay, and the closed loops are used especially for automatic control. And well, but in this video we are going especially of we're going to talk about especially of open loops. Okay, so we're going to talk about open loops. So one of the main aims of control theory is to determine a control such that the corresponding output has a desired property. That's the aim. We want to determine a control such that the output has a determined property. So considering that, we're going to talk about two basic classical concepts of control that are controllability, and okay, observability. Okay, so we can mention something about controllability to give us an idea. Controllability. Okay, controllability. Okay, one says that a state C, element of Rn, is reachable from an initial state x in time t, if there exists if there exists, this is important, if there exists an open loop such that for the output, that is the solution of the differential equation, y, we have that y of t is equal to c. Okay, so graphically, how can we represent this? We have again an input, then I assume that I have a control function. So the question is it exists? Well, then if I assume that I have that function, then I have a process. That in this case is my differential equation. Okay, then I have an output that is the solution of that differential equation with an input. That input, it was an initial state. That basically is an initial condition. An initial state is an initial condition. Okay, and I have an output. I have a solution. An output. So we call that the state C is reachable if I can determine this control. If I can determine this control such that in the initial time is equal to the initial state, and the final time t is equal C. Okay, so we are obtaining an idea of how of this works. Okay, so we are going to give other concepts. If an arbitrary, it could be whatever. If an arbitrary C is reachable from an arbitrary state, initial state x in time t, in a finite time, in finite t, we say that this system, the system, what was the system y prime equal f y u is controllable. Okay, so we have a basic concept about this. So we're going to talk about now about classical control theory. Okay, the basic object of classical control theory is a linear system, system described by a differential equation of this type, by a differential, give me a moment, by a differential equation of this type. The derivative of y respect to x, no, respect to t. Okay, respect to t. Okay, respect to t is equal a y of t plus b u of t. Okay, and I'm gonna name it a star. because we are going to call it later. So y of 0 is equal x element of Rm. Okay, and we're now we have also an observation relation and observation relation wt equals c y of t, where t is greater or equal than 0. Okay, where in this case where the linear transformations, where the linear transformation A goes Rn to Rn, B goes from defined on Rn to Rn, and C defined on Rn to Rk will be that, and this is important, will be identified with representing matrices, with representing matrices. Okay, so basically we are working with matrices, well, with linear transformation, but they will be identified with representing matrices. Besides an arbitrary function, you define on this interval to Rm local integrable, and this is important because later we are going to define some concepts related with integrals, so it's important that the function is locally integrable. So an arbitrary function u locally integrable will be called a control strategy or input of the system, of we mentioned before, or input of the system, or input of the system. Well, I know we have also more notation. Also, the corresponding solution of the system, the solution of the system star will be denoted by y to the power of x u to underline the dependence of the initial condition and the input of control function that we are using. So the observation relation is now w of t equals c y to the power of x comma u of t, where t is an element of the intervals that goes from of the interval 0 t. Okay. The function w is the output of the control system. This function w is the output of the control of the control system. For the moment, we are going to suppose that this matrix is the identity. We're going to suppose for the moment that this matrix is the identity. So we have the output or the observational relation is W of t equal y of x u of t for t greater or equal to 0. Okay. So as we mentioned before, we say that control you transfer a state A to a state B at time t greater than 0 or positive if the solution with initial condition equal A and control U in the time elated in T uppercase is equal B. So we related the concept for the general equation. So now we are going to define the controllability matrix because this matrix will be useful in a theorem. Now we define the controllability matrix as qt equal the integral from 0 to t s of r b transpose s transpose of r dr, where t is a positive number. Okay, where, as I mentioned, where b star denote the transpose matrix of B and S of R is simply the exponential matrix. Okay. So we have now our first important theorem because it shows us how the control has to be in order to reach a determined state, final state. Okay, so theorem. So we have our first theorem. Okay. Assume that for some t, t positive, the matrix qt is non-singular. Then for arbitrary A and B, initial and final state element of Rn, the control, we have a special control. I don't know how to say it. We will say U hat. U of S equal minus B transpose S transpose of T minus S QT inverse multiplied by S of T A minus B, where S is an element of the interval 0t, transfer transfer A to B at time t. Oh, wow. So we have, before we have this, the equation, did it exist a control? Now we have at least a control for that, such that A is transferred to B in a finite time. So I have this control. So we are going to prove that. We are going to prove that we can transfer A to B at finite time. Okay, so proof of this. Okay, give me a second. Proof. We know we already know that the solution of the system, derivative of y respect to t equal a y of t plus b of t with the initial condition y of 0 equal a, and a is an element of Rn, is given by y of t equal xt x0 minus 1 a plus the integral, or the inverse of x t evaluated in 0, plus the integral from 0 to t xt, the inverse of x evaluated in s, bs, ds, and t greater or equal than 0. We have that, well, for that system, this is the solution. Where in this case, we know that this is a fundamental matrix, and in this case, we are going to take bt as bu hat of t. Okay, and the fundamental matrix is gonna be the exponential matrix that we know that is a fundamental matrix. Okay, fundamental matrix. So then we have the following. We have that the y to the power of a u hat evaluated in t uppercase is equal to a plus the integral from 0 to t a minus a minus as a. Okay, that's good. B you had s ds. Okay, but this, we know that is the fundamental matrix, the exponential in a time t. So we have this is s of t a. Also we replace the control that we have. We replace this control, all of this, because we want to prove that this transfer a to b at time t. Okay, so we replace where I have u hat. I'm going to replace that for this expression. So we have minus the integral from 0 to t s of t, other thing, we know that this is t minus s of a. Okay, t minus s ln t minus s. Okay. B transpose s transpose t minus s, the inverse of qt multiplied by st a minus b ds. Okay, and this is equal to st a minus the integral from 0 to t st minus s b transpose s transpose t minus s ds, and this is in this integral. This is a constant. We can take this expression out of the integral. So we have qt inverse s t a minus b. Okay. Now we consider the following change of variables. Key equal t minus s, so the key is equal minus ds. From this we have ds a plus t 0 s key b transpose s transpose key d key t key qt inverse s of t a minus b. Okay. Now, using a property of the integrals, we can change the limit, and we have s of t a minus 0 t s key b key transpose s transpose key d key qt inverse s t a minus b. But we know, or we can notice that this is the controllability matrix. Controllability matrix. So this is equal as sta minus qt inverse st a minus b, but we have that this is the identity, so this is s of ta minus s of ta minus plus b. We cancel, and then we have that this equals to b. So finally, u to the power of x u with this control in evaluated time t is equal to b, and this is exactly what we want to prove. So this control transfer the initial state, okay, this is a, the initial state a to a final state b in a finite time t. Okay, so we have our first important result. So now we are going to have another concept next, and this is the important concept you have to consider. So we say that a state B is reachable from a element of Rn initial state, where this is the initial state. This is the initial state if it's reachable at some time t, at some really finite time t. positive. Now the system, this system, derivative of y with respect to t, a y of t plus b, the control u of t, is called controllable, if an arbitrary state b, that means whatever final state I want, is reachable from any state, a element of Rn at some time t, at some finite time t, at some time t greater than 0. So we usually say that the pair, and we have a special notation for this. We say that the pair, we usually say that the pair AB for these matrices, transformation for these operators, we say that the pair AB is controllable. Okay. Now we have other concepts. Now that it was in this concept, the only it does matter is that this time t exists. But if we can, if arbitrary state can be reachable at the term always in a determined time, this system is called controllable at time t. So if for arbitrary a and b element of Rn, the system reach the solution, the final state at time t at a given time, t greater than 0, we say that the system is controllable at time t. So in this case, I give the time. If a system satisfies this condition, we say that the system is controllable in a finite time t, always greater than 0. Okay. Well, the previous theorem that we showed, the previous theorem that we showed, give us a sufficient condition for the system to be controllable. Now, it turns out that this condition is also necessary one, that it's another theorem that we don't prove it because it's not necessary. We also prove the necessary the important theorems, but we want to mention the result. If an arbitrary state B element of Rn is reachable from 0, then the controllability matrix the matrix, then the matrix Qt is non-singular. Is non-singular for an arbitrary t greater than 0 or positive. So if an arbitrary state is reachable from 0, from initial state 0, the controllability matrix is not singular. Wow, that's my important result. So now we are going to define a useful operator. A useful operator. Now we define a useful operator let for a control u and t positive, the linear operator LT defined in this space L1 0T to Rn to Rm defined by LT of a specific control is equal to the integrals from 0 to t SR B U of t minus R dr. Okay, it's simple. Notice that, note that this LT of U is simply the solution at time t. Is the solution at time t of the system. Always the system consider this control, and the system that have an initial state consider of 0. Okay. So now we have a remark. Okay, remark. Well, this is notice that this theorem is valid when, and the previous theorem was valid when the system, when an arbitrary final state B is reachable from 0, but it could be for whatever other initial states. So remark, if an arbitrary state B element of Rn is reachable from 0, then system is controllable. Then system is controllable. That means that reachable from A to B at time t. It's sufficient. Know that the solution of the system when the initial condition or the initial state is A and we have the control U at time t is equal to L of TU plus the exponential matrix evaluated at time t multiplied by the initial condition A. And that's simple. We only have to note that this is valid. Okay. Well, we have a sufficient condition to the system to be controllable. Now we have another important result that is related with the rank of a specific matrix. So we discuss now about the rank condition. rank condition. What does it mean? What does it mean? Now we formulate an algebraic condition equivalent to controllability. So let A n times m matrix and B n times m matrix. We denote this matrix A, B, the m times m multiplied by m matrix defined by B, AB, A squared B until A to the power of n minus 1 B. Okay, which consists of consecutively written columns of matrices B, AB, A squared B until A to the power of n minus 1 B. So we have one of the most important theorems of this video that is called the Coleman rank condition. So we have a theorem. We have the theorem Coleman rank condition. So what is the Coleman rank condition, or what does it say? System, it says that system derivative of y with respect to t equal a y of t plus b u of t with the initial condition y of 0 equal x, and this x is an element of Rn, is controllable if and only if the rank of this matrix is equal to m. So I take this matrix, I take the other matrix B, I use or I construct this AB matrix, and if the rank of this matrix is m, the system is controllable. But we need some previous result or other things to prove it. So we're going to define other things. So first, we define a linear operator, a linear operator Lm, where Lm is defined on the product of Rm times Rm n times. Well, and this from this set to Rm. Well, given by this rule, given by Ln of u0 until un minus 1 is equal to the sum from j equals 0 to n minus 1 a to the power of j b u j, where j is an element of Rn and j goes from 0 until n minus 1. Okay. And well, from this operator, we could deduce some properties of the matrix AB. So we're gonna, to deduce some of the properties of this matrix, we are gonna use this linear operator. So also we have to remember, also we remember theorem of linear algebra. We remember the the Cayley-Hamilton theorem. A with a characteristic polynomial P of lambda equal lambda to the power of n plus a1 lambda to the power of n minus 1 plus until an, where lambda it's a complex value. We have that the characteristical polynomial evaluated in the matrix A is equal 0. So we prove that we have proved that in linear algebra. So we don't need a proof for that. And well, we're gonna prove a lemma that this is the main important lemma for the proof of the Kalman rank condition. So what does this lemma say? What does the lemma say? The transformation LT, where T is positive, has the same image as LM. In particular, LT is onto if and only if LM is onto. Well, so we start with the proof. So we're gonna note something. So for arbitrary B element of Rm, U element of L1 0 T Rm, where Uj is an element of Rm, J goes from 0 to n minus 1, we have the following. We have the inner product of L, T, U, and B is equal, by definition of LTU, of the integral to 0 from 0 to T of SR B U T minus R dr B. Well, we now consider a change of variable. We consider the change of variable as T minus R. So the ds equals minus dr in order to change these arguments. Okay, so using that change of variables, I have that changing that, I have the integral from 0 to T S T minus R B U S ds B, and we can take the integral out of the inner product. We can prove it, but we assume that here because we don't have enough time in this video, so we can take the integral without problem. This is the integral from S T minus R B U S B ds. Okay. Well, other thing that we consider in this video is that when I have the inner product of x and y, this is equal to x transpose multiplied by y. So we consider this in all of these videos. So this is the integral from 0 to t as t minus r b u s transpose b ds. And well, we use some of the properties of the transpose of a matrix. So this is equal to the integral from 0 to t b u s transpose s t minus s transpose b ds. Okay, and this is equal to the integral from 0 to t u us transpose b transpose s t minus s transpose b ds. Okay, and this is equal to the integral from 0 to t us b transpose s t minus s transpose b ds. So we have the following. And this is the first remark that I want to show you, that the inner product of LT of U B is equal to the integral from 0 to t US B B transpose S T minus S transpose B ds. And well, also I want to show you another remark, but now considering the LM function. So also the inner product of LM evaluated U0 until UN minus 1 B is equal by definition of this operator to the inner product of the sum from j equals 0 to n minus 1 a to the power of j b u j b. And well, I can take the sum out of the inner product, so I have the sum that goes from j equals 0 to n minus 1 of this. Well, again, we do this calculation and have the following. Okay. We do j converse b. Okay. Okay. And this is equal. And this is equal to the sum from j equals 0 to n minus 1 b uj transpose a to the power of j transpose b, and this is equal to the sum over j equals 0 from n minus 1. In this case, I have j u j transpose b transpose a transpose to the power of j b, and this is equal, again by definition, well, not a definition, simply by the consideration that this is this, and then we have that the sum from j equals 0 to n minus 1 of j of the inner product of uj and b transpose a transpose to the power of j b is this. So what we get? Ln un minus 1 b equal the sum that goes from 0 to n minus 1 uj b star a transpose j b. Well, and we are going to use these expressions in the demonstration of the lemma. So now we are going to prove that the image of the LT and LM are the same. We are going to prove that the image of LT and the image of Ln are well, we prove this, that these images are equal. So now, so we should prove that the image of this is contained, well, I could prove it in this way, and this is contained in the image of LT. But notice the following. So now suppose that this LU0 until UN minus 1 B, the inner product of this is equal 0 for arbitrary U0 until UN minus 1 element of Rm. What does it mean? It means that B is an element of the image of Ln of the complement of the orthogonal complement of the image of Ln. Then if I have that this if I have that this is equal 0 for arbitrary U0 until UN minus 1, and I know that this is equal to this sum, so I have that this expression have to be 0 because I am taking arbitrary uj. So then B transpose B is equal 0 until B transpose A transpose to the power of n minus 1 B is equal 0. So well, I have this for the moment. Next, by the Hamilton theorem, we have that a transpose n plus alpha 1 a to a transpose to the power of n minus 1 plus alpha n, the identity is equal to 0. So I can take all of this to the other side of the equation, and I have all a transpose to the power of n is equal to the sum of key equals 0 and minus 1 ck some constant a transpose to the power of key. And well, this is a result from the Kelly-Hamilton theorem. Okay. Now we prove something related with this. I have that this is valid for a transpose to the power of n. But I would like to prove that this is also true when I have when I have a that this is equal to some constant. That is the thing I want to prove is that if I take the power of any power of this matrix, this can be expressed of a finite sum. So we consider the following. It's simple C. It's simple C that by induction, obviously, by induction for arbitrary L that goes from 0 to, well, all the natural numbers, including the 0, that exists constants CL0 until CL n minus 1, such that a transpose to the power of n plus L is equal to a finite sum of key equals 0 to n minus 1 of CL key a to the power of the a transpose to the power of key. Well, but this is simple because we only use repeatedly the Hamilton theorem and rename the CL constant. Well, we write this. We only use repeatedly. The Hamilton theorem and rename the CL key constant. Okay. When L is equal to 0 is only the use of Hamilton theorem, and we prove. So suppose that this is satisfied. We suppose that this this, I'm gonna call it, I don't know, two star. Suppose that 2 star is satisfied. It's satisfied to L. Now we prove it to L plus 1. Okay. So give me a minute. Okay, to L plus 1. So we have a transpose n plus L plus 1, but this is equal to a transpose multiplied by a transpose L plus L. And by hypothesis, I have that this is equal finite sum. This is equal finite sum from key equal 0 to n minus 1 to CL key a to the power a transpose to the power of key. And this I can multiply. I can multiply this with this, and I have key equals 0 to the power of n, the sum from key equals 0 to n minus 1, CL key, A transpose, key plus 1. Okay. And now only I have to separate, I only have to separate the sum over key equal n to n minus 2, CL key, A transpose, key plus 1, okay, plus CLN transpose to the power, transpose of A to the power of n. Now we apply the Cayley-Hamilton theorem to this part. So that's why I said that is the use repeatedly of the theorem. So now applying the Cayley-Hamilton theorem, we have the same sum in this part. I have the sum that from key equals 0 to n minus 1, CL key, A transpose to the power of key plus 1, plus CL minus CL n minus 1. I replace this expression by the corresponding finite sum. The sum I equals 0 to n minus 1, Ci, A transpose to the power of I. And we notice that these two sums is the sums of is the sum of two of expression until A to the power of n minus 1. So it's simple that we can rearrange the sum in the way that we have the sum from key equals 0 to n minus 1. Also, we have to recall. Also, we have to recall all of these, because we multiply this by this. If I expand all the sum and take factor commons and something like this, I have to rename all of these coefficients. So I will call it CL plus 1 key to A transfer to the power of key. Well, and I have that result by induction. This is simple. This is something simple. Okay. Considering that is true for whatever else, then so considering that therefore B transpose A transpose to the power of key B equals 0. We know before that these expressions were 0, but only when key was between 0 and n minus 1. But with this, with the expression previous before, we could extend this to whatever exponential here. So this is true for key element of the natural numbers including the zero. So this is important. And I have now the result that this always is zero. Next, taking into account that B transpose S transpose T, B is equal to B transpose. Remember that S simply is it's only the exponential matrix, so I use the definition, the zeros from 0 to infinity. T to the power of k factorial, A transpose to the power of k multiplied by B. And well, I can enter this and this in the series, and I have the series that goes from k equals 0 to infinity. B transpose, A transpose to the power of k, B and T to the power of k factorial, and this is valid when T is greater or equal than 0. So, but remember, I just said that this is 0, so this is gonna be 0, and obviously this is gonna be 0. That's why we want to prove that. Perfection. Okay, so we deduce that for arbitrary T greater than 0 and T element of this interval, we have that B transpose S transpose of T, B is equal 0. But we remember why this is important. Why is this important? Because I remember that when I have the inner product of LTU and B, I have that expression here. Oh, okay, I have that expression here. And now I know that that expression is 0. Perfect. So I have the inner product of LTU B is equal to the integral from 0 to T US, the integral of the inner product of US and B transpose S transpose T minus S B ds, and I just proved that this is 0, so this all of this is 0. For arbitrary U element of this space. But what is this? It means that B is also an element of the orthogonal complement of LT. So what have we proved? We proved that the image of Ln orthogonal complement is a subset of the image of the orthogonal of the orthogonal complement of LT. Okay, now I prove the other inclusion. Conversely, assume that for arbitrary, u element of L1 0 t to Rn, this inner product is equal to 0. What does this mean? That B is an element of the orthogonal complement of LT. Okay. Then, as I said before, we have that this is equal to 0 for T element of this interval. So, okay, now differentiating the identity, this identity, the series from key equals 0 to infinity, B transpose A transpose to the power of key, B, C key, key factorial is equal to 0 for T element of this interval. How many times do I have to differentiate this? 0, 1, until n minus 1 times. And inserting each in t equals 0, then we have the B transpose of A transpose to the power of key B equals 0 for key that goes from 0, 1 until n minus 1. Therefore, by the remark that we said at the beginning of the proof, I have that this inner product is equal to 0 for arbitrary u0 until un minus 1 element of Rn. So, but this implies that the image of LT, the orthogonal complement of the image of LT is a subset of the image of the orthogonal complement of the image of Lm. So in this way, by the direct way, I have therefore I have that the image, that the orthogonal complement of this image is equal to the orthogonal complement of this image, but this also implies that the image of LT is equal to the image of Lm. So I have proved the theorem that these two operators have the same image. So now we return to our principal theorem. That was the Kalman rank condition. Okay. System. Give me a minute. Okay, give me a minute. Okay. Okay. So, sorry for that technical issue. Well, but we proved that the image of these operators were the same. Well, so we return to our principal theorem of this section, and this is the Kalman rank condition. And I have the Kalman rank, and I have the Kalman rank condition. Okay, give me a minute. 1 second. Okay, we continue. Okay, the theorem is the following. System derivative of y respect to t is equal to a y of t plus b u of t, y of 0 equal x is controllable if and only if the rank of this matrix is equal to n. So we have the following. So proof. Assume that the system is controllable. Assume that the system is controllable. Assume that the system is controllable. Then the transformation LT is onto Rn for arbitrary t greater than 0, and by the previous lemma, the matrix AB has rank m. Well, that's all. For the conversely, if the rank of this matrix is equal n, then the mapping Ln is onto Rn, and also by the previous lemma, and also the transformation LT is onto Rn, and the controllability follows, and the controllability follows. Okay, and that's the proof of the theorem. So we have with this theorem we can prove other theorem that is very important, but it's too large for this video. So we only initiated and we use it in the next section. So it says that theorem. The following, it says that the following conditions are equivalent. The following conditions are equivalent. So, one, an arbitrary state B is an element of Rn, an arbitrary state element of Rn is reachable from zero to system AB is controllable. Three, system AB is controllable at a given time. Is controllable at a given time. T positive. Four, matrix Qt is non-singular for some T positive. Five, matrix Qt is non-singular for an arbitrary T greater than 0. And 6, that is really the Kalman rank condition, is that rank of this matrix AB is equal M. Well, as we said, the proof of this is very simple because it's only the use of some of the theory that we have shown or that we have mentioned before. Like, for example, this and this is the Kalman rank condition. The necessary part of the first theorem is this implication. This is clear. System is controllable time t is controllable. Also, if it's controllable at a given time t is non-singular. So to prove this, it's only necessary to use all of the theorems and the thing we have mentioned until now. So that's some of the things related with the part of controllability. So we mentioned a little things about observability. Okay. The observability of a control system is the ability to determine the internal state of the system by observing the output in a finite time interval when input is provided to the system. The question about observability. The question is can you predict the initial state of the system? Can you predict the initial state of the system by having the knowledge of the input of the input and output is yes, then system is observable. If the answer of this question is yes, if yes, then we say then system is observable. So if I have the knowledge of the input, so the control, I have a control. I know the output of the system. Can I predict the initial state? If the answer is yes, system is called observable. Well, so it's important to mention that both controllability and observability are dual of each other. Okay, besides the observability is only dependent of the coefficient matrices A and B. Is only dependent of the coefficient matrices A and B. So we can simplify. Our state equations to remove the input, the control. So to remove the input term, Okay. So now we assume that B is equal 0 because the observability only it doesn't depend of the input that we have. Assume B is equal 0, then we have the system. C prime equal AC, C0 is equal X, and I'm going to call this star, and the observation relation W equals CC. Well, we denote the solution. Of a star by CXT, where T is greater or equal than 0, and obviously this matrix is constant. So obviously this solution C to the power of X T is S of T X an element of Rn, where this f of T is an exponential matrix. Now, okay. Now the system C prime equal AX with initial condition and the observation relation, or simply denoted by this pair AC, is said to be observable. if for arbitrary x different from 0, but x an element of Rn, there exists a t positive such that W of t is equal c to the c to the power of x t, and this is different from 0. Well, now note that the situation here is that we want the existence of this t, but as controllability we can say that a system is observable at time t if in the interval 0t there exists that t, that t. We write it. If for a given t greater than 0 and x different from 0, there exists a t element of this interval with the above property, then system AC is said to be observable at time t. Okay. So if I have a given time and the system and I can find a t in this interval such that the solution is different from 0 in that t element of the interval 0 t uppercase, then the system is called observable at time t. And well, we can we can mention something that it could be so simple to show. Remark. If a system is AB, if a system AC is observable, then it is observable. It's observable at a given time, at a given time t positive. Now, remember that when we were talking about controllability, we have the controllability matrix. When we talk about observability, we also have an observability matrix. So we introduce the observability matrix. And this matrix is the interval from 0 to t S transpose of R C transpose C R T R. Well, but this observability matrix has something interesting related with the controllability matrix. Note that the observability matrix of AC is the same of controllability matrix of this system of A transpose B C transpose. Well, And this is very simple to, and see, this is very simple because RT is equal to the integral from 0 to t S transpose of R C transpose C R dr. But this we have applying some properties of the exponential matrix. We have that this is A transpose C transpose C transpose transpose A transpose transpose, and this is equal to QT. Well, now we characterize in some way when a system is observable. So we have a little theorem here. So we have a theorem. So give me a minute. Okay, theorem. Okay, theorem. System AC is observable. System AC is observable at a given time. At a given time t greater than 0, if and only if the matrix RT is non-singular for arbitrary C for arbitrary t, obviously greater than 0, no? Okay, proof. For the proof, we have to note first something. Note that the integral from 0 to t of this is dr is equal to the integral from 0 to t of the modulus of c to the power of x r squared dr. But this norm really is the inner product of this with itself. So CSR x, that, because that's the definition of this, we inner product with this with itself as R x dr, and we apply again the use of the inner product that we have used in this video. 0t C S R x transpose C S R x dr. Okay. And this is equal to the integral from 0 to t. We apply some properties of the transpose, and we have CR x transpose CR transpose C transpose x dr. Okay. Okay, yeah. The integral from 0 to t. Again, the property of the transpose, and we have the following. We have this, and then we have C R transpose C transpose C CR x transpose x dr. And this is equal to the integral from 0 to t, the inner product of CR transpose C transpose C CR x there, and we can I don't know, enter the integral. I don't know how to say it, but I'm going to say it in that way. Enter the integral to the inner product, integral from 0 to t, C SR transpose, C transpose, C R dr x, but we have here the controllability, no, the observability matrix. Okay. And this is equal to RTX x. So we have the integral from 0 to t, the modulus or the norm of the W R to the square dr equal to the inner product of RTX x. Okay. Now we give now we prove the theorem. The theorem system AC is observable at a given time t is only if the matrix RT is non-singular for arbitrary t greater than 0. Okay. So in the direct way. Okay, suppose AC is observable. Suppose AC is observable at a given t greater than 0. Then there exists t element of this interval such that W of t equals c to the power of x. T is different from 0 for arbitrary x different from 0. So the inner product of RTX x that is equal to this integral is different from 0. This implies this this is valid when x is arbitrary and different from 0. So this implies that RTX is different from 0 when x is different from 0. Okay. So this implies therefore the only solution to RTX equals 0 is x equals 0, and we have the non-singularity of the matrix. So RT is non-singular. Is non-singular for arbitrary t. Okay. Now, conversely, suppose RT is non-singular, suppose RT is non-singular for arbitrary t positive. Then again by the previous part, we have then RTX is different from 0 for x different from 0, and this implies no by the previous part, only because it's not singular. So this implies that RTX is different from 0 for x different from 0 because it's not singular. The only solution for this is x equals 0. So then I have the RTX is then different from 0. So this integral. So this integral is different from 0. So if this integral is different from 0, and this integral is positive, so we have, therefore, WT is different from 0 for some t element of 0t. So AC is observable at a given time, t positive. And that is the proof of the theorem. Well, using this and the previous and some of the previous theorems that we have mentioned, it's simple proof those two theorems that are useful sometimes, especially when we have problems. So theorem. So I don't have enough time to prove them, so I'm only gonna say them. Okay. Theorem AC is observable. AC is observable if and only if this is controllable. And why? Because remember that RT in this system is equal to QT in this system. And the proof is very simple. So we only have to consider this. And well, AC is observable if and only if this system is controllable. And we have a corollary that AC, a system is observable if and only if the rank of this matrix AC C is equal n, which is the common test. And this is simple because this system by the Kalman rank condition is controllable if and only if the rank of this matrix is equal n. So, and that implies the corollary. So it's really simple. We finish with an example. We finish the video with an example. So imagine I have this system x1, x2, x3 prime equal -2, -2, 0, 0, 0, 1, 0, -3, -4, x1, x2, x3, and the relation and the observation relation 1, 0, 1, x. Then we have that this matrix. This matrix is equal to this matrix CA square, and this matrix I did the direct calculation. 1, -2, 4, 0, -5, 16, 1, -4, 11, and we can verify that the rank of this matrix is equal 3. Okay, so since the rank of this matrix is 3, then this system AC is observable. How simple is that? And well, that's all for this video. I hope you like it. Bye. Okay.